Hello and welcome to my talk. My name is Wiebke Middelberg and I'm a PhD student in the signal processing group at the University of Oldenburg. In this video, I represent the work of Simon Doclo and me about joint noise and interferer reduction using MPDR-based GSC structures that incorporate hearing aids and additional external microphones. Enjoy the talk. So let me first give you a short outline of my talk. We start with the acoustic scenario and the problem at hand. After that, we come to some processing strategies that we use only for the hearing aid devices and also for incorporating the external microphones. Then we come to the evaluation of the considered algorithms. And last, of course, I'm going to give you some conclusions and an outlook of future work. We consider a scenario where there is a hearing impaired person equipped with hearing aids who wants to listen to a target speaker. But as we all know, real-life scenarios aren't so simple, but there's background noise and interfering speakers will lead to a lower intelligibility of the target speaker. So particularly for hearing impaired people, we need to reduce the background noise and the interfering speech to allow to listen to the target speaker again. So our overall goal is to achieve joint noise and interferer reduction. If we now use a system like this, where we have the hearing aids and we steer a spatial filter, that is a beamformer, in the direction of the target speaker, we can achieve some noise and interferer reduction. But the performance of such a system is rather limited, as we have only a small number of microphones available, and also the spatial sampling of these microphones is rather limited, as they are all placed around the head of the user. So it has been shown in literature that including external microphones into speech enhancement algorithms actually can lead to a better performance. So by including these external microphones into our beamformer, we can actually achieve even more noise and interferer reduction. However, it is now the question how we actually incorporate these microphones. And this will be the main task that we focus on in this presentation. In the following, we come to some processing strategies which are based on the generalized side lobe canceller. Once, the local GSC, which only uses the hearing aid microphones, and in the second step, an extended GSC structure, which also incorporates the external microphones. But before we can do that, we first have to define our signal model and notation. We define our signal model in the short-time Fourier transform domain, where we stack all M available microphones into our signal vector Y, which means that it contains both the hearing aid microphone signals and the external microphone signals. In this vector notation, we can write the noisy input vector as the sum of the target, interfering, and noise component. For the target speech vector, we can write it as the target speech component in a reference microphone, multiplied by the so-called relative transfer function vector, or short RTF vector, which relates the target speech component in the reference microphone to all other microphones. And this is now a very central quantity in our talk, as we needed to steer a beamformer in the direction of the target speaker. For those of you who are not too familiar with this concept, you can imagine it as a generalization of a steering vector in beamforming applications. We can also realize that we can write this RTF vector as the local RTF vector for the hearing aids and the external RTF vector. Furthermore, we can define the second order statistics of our signal as the noisy covariance matrix, which is equal to the sum of the target, interferer, and noise covariance matrix if we assume statistical independence of the different signal components. We now consider the target speech covariance matrix, which is a rank 1 matrix spanned by the RTF vector and scaled by the target power spectral density. If we now want to extract this target RTF vector from our noisy input covariance matrix, we have to realize that standard estimators can actually just account for the influence of the noise component, but not for the influence of the interferer. So by means of standard estimators, we cannot extract the target RTF vector, which is therefore not available for us. So we now have to make some assumptions, as we cannot blindly estimate our target RTF vector. And the first assumption that we make is that we know the geometry of the hearing aids, or rather saying the spacing of the microphones within it. However, we also have to stress that this assumption really only holds for the hearing aid microphones, but not for the external microphones, as they might be placed anywhere in the physical space, and therefore their relative position is unknown. We also assume that we know the relative position of the target speaker to the listener, which is also often done in hearing aid applications, where it is, for example, assumed that the target speaker is located in the look direction or in front of the listener. And with these two assumptions, we can also assume that we know the RTF vector for the hearing aids, or at least that an estimate is given. So we can now exploit this piece of information to steer a beamformer. However, if we also want to incorporate our external microphones, we cannot make this assumption, and we still have to estimate them. Okay, and we now want to focus on how we can exploit this a priori RTF vector for the hearing aids and blindly estimate the RTFs for the external microphones despite the presence of the interferer. First, we consider the standard generalized side lobe canceller, which is often used in hearing aid applications. Also in our case, we apply this beamformer only to the local microphones or to the hearing aid microphones. And we also exploit our a priori RTF vector, in this case to steer a fixed beamformer in the direction of the target speaker, which creates the so-called speech references, YF. And we also exploit the a priori RTF vector to create a blocking matrix, which aims at canceling the target speech components. That means it only leaves us with the signals UA, which ideally only contain noise and interferer. That's why we call them the noise and interferer references. The last building block of the local GSC is this adaptive filter, VA, which aims at canceling the correlated components between our noise and interferer references and the speech reference. For this adaptive filter now exists a variety of design choices, where we want to focus on the difference between the implementation as a minimum variance distortionless response, or short MPDR beamformer, which only aims at canceling correlated components between the noise and interferer references and the speech reference. And as a second option, we want to investigate the minimum power distortionless response beamformer, or short MPDR implementation, which also aims at canceling all correlated components, meaning also the interfering component between the noise and interferer references and our speech reference. So this is actually the choice that we need to make here to achieve also active interferer reduction. However, it has also been shown in literature that an MPDR implementation is more sensitive towards RTF vector mismatches, meaning that if this a priori RTF vector here is not ideal, it might actually be that some target speech leaks into our noise and interferer references, and that the adaptive filter, in the case of an MPDR implementation, actively cancels the target speech components. Now we know how to exploit the a priori RTF vector. However, the question remains how to incorporate the external microphones into the processing. And the first approach would be to use a joint MVDR, or respectively MPDR beamformer, which uses the output of the local GSC and the external microphone signals. However, this beamformer requires an estimate of the external RTFs, which strongly depends on the signal to interferer ratio, meaning that the more interferer there is in the signals, the worse this estimate will get. So now we can regard this local GSC as some sort of pre-processing of the hearing aid microphones, where we obtain a signal which ideally has a higher signal to interferer ratio than the input signals. And something similar we can actually also do for our external microphones. So now we pre-process these external microphone signals by means of a set of adaptive filters which aim at cancelling the correlated components between our noise and interferer references and the external microphone signals. In 2019, Randall Ali proposed this structure. However, he used an MVDR implementation for noise reduction tasks only. But in our case, as we specifically aim at reducing the interferer in the preprocessed external microphone signals, we propose to use an MPDR implementation. But again, we have to pay attention here that in the case of an RTF vector mismatch of the a priori RTF vector, and therefore we might encounter speech leakage. In these cases, or in this case, the adaptive filters might actually also cancel target speech components, which would be undesired. With this, we now come to the evaluation, where we want to investigate three main factors. The first is the benefit that we can achieve by incorporating the external microphones into our processing. The second one is the difference between MVDR and MPDR beamformers. And the last one is the influence of mismatches of the a priori RTF vector. The evaluation was performed with real-world recordings with a reverb time of about 350 milliseconds and binaural hearing aids mounted on a dummy head and two additional external microphones. The target speaker was the male on the right side of the dummy head, and the interferer was a female speaker on the left side of the dummy head, both in a distance of about 2 meters to the listener. The background noise was created by 4 loudspeakers facing the corners of the room and playing back multi-talker babble noise, which created a quasi-diffuse noise field. All signals components were recorded separately at a sampling rate of 16 kilohertz. All processing was implemented in the STFT domain, where we used a batch estimation of the covariance matrices using an Oracle voice activity detection. For the adaptive filters, we used the closed form Wiener filter solutions. The parameters of the STFT framework were an FFT length of 1024 samples, where advanced frames overlapped by 50%, and they were windowed with a square root Hahn window for analysis and synthesis. The conditions that we investigated were a fixed input signal to noise ratio of 0 dB, an input signal to interferer ratio that varied from -15 to 15 dB, and 2 a priori RTF vectors for the hearing aids, once an ideal one coming from the room impulse response, and a non-ideal one coming from an anechoic database steering in the direction of the target speaker, which allows us to investigate the influences of RTF vector mismatches. For the estimation of the external RTFs, we used the standard method covariance whitening. The metrics that we investigated were the signal to noise ratio improvement, delta SNR, and the signal to interferer ratio improvement, delta SIR. We now come to the results of the evaluation. The 4 algorithms that you see here are the local GSC in blue, which only uses the hearing aid microphones, once as an MVDR and once as an MPDR implementation with a dashed line. Furthermore, in green here, we have the extended GSC structure, which also incorporates the external microphones, again, as an MVDR with a solid line and an MPDR with a dashed line. So in this first panel here, you see the case of an ideal RTF vector for the hearing aids, where we plotted the SIR improvement over the input SIR. And what you see here, particularly at low signal to interferer ratios at the input, is that the MPDR implementation of both systems, the local GSC and the extended one, perform much better than the respective MVDR implementations. However, at high signal to interferer ratios, this difference becomes very small. Now, in terms of SNR improvement, we see that the system in green, which includes the external microphones, performs overall better than the local GSC, which only uses the hearing aid microphones. So the main conclusion that we can draw from this is, first of all, that the incorporation of the external microphones allows for better noise and interferer reduction than only using the hearing aid microphones. And we can also conclude that the MPDR implementation leads to better interferer reduction, particularly here at low signal to interferer ratios. If we now look at the case of a non-ideal RTF vector, which simulates an RTF vector mismatch, we can see that in terms of SIR and Snr improvement for the MVDR implementation, so the solid lines, the changes are not so large. So the results are actually rather robust. But more interestingly, we can see for both MPDR implementations of the local GSC and the extended GSC that at high signal to interferer ratios, we actually end up with negative scores. And also in terms of noise reduction, it actually doesn't perform well, while at low signal to interferer ratios, still performing a lot of interferer reduction. This actually can be summarized by saying that the MPDR implementation is less robust against RTF vector mismatches, particularly at high signal to interferer ratios, where speech leakage becomes more prominent. To wrap up the talk, we now come to the conclusions. First of all, we could see in the evaluation that incorporating the external microphones actually leads to better noise and interferer reduction than using the hearing aids alone. Furthermore, we could also see that an MPDR implementation leads to better interferer reduction than an MVDR implementation, particularly at low signal to interferer ratios. However, we could also see that at high signal to interferer ratios, an MPDR implementation of the considered algorithms is actually more sensitive to RTF vector mismatches due to speech leakage. So what we would like to consider as an outlook is an SIR dependent system where at low signal to interferer ratios, we would like to use an MPDR implementation such that we actually cancel the interfering speaker. However, at high signal to interferer ratios, we would like to benefit from the robustness of an MVDR implementation. And with this, I would like to close my talk and thank you for your attention.